Hello. Next up, we have Matheus Cardoso. Matheus is an iOS engineer and an open source enthusiast from Brazil. Currently, his mission is to bring Apple-grade security to the hands of the average developer, which I guess is us.
Hey, thank you. Thank you for the introduction. So my name is Matheus Cardoso, and I'm a developer relations engineer at Virtual Security. And I also do some open source stuff on GitHub. But on a daily basis, I actually help developers and founders build secure applications for the healthcare market. And what they generally want is some form of secure storage, secure transmission of messages, and also password protection. And they want this mainly because of health data breaches, which can be really, really expensive. And I suspect some of you here are either building or have the idea to build some healthcare app, or maybe you work at a dev shop that might need to build some healthcare app at some point. So I'm here to expose a few concerns around building these kinds of apps, mainly the issues of security, what are the cryptography tricks that you can use, and about the regulations that are in place, and overall what you need to keep in mind to get into this market. So the healthcare market in the US is big. It's almost $4 trillion a year overall, and that grows 5% every year. Last year alone, more than $23 billion were invested in healthcare startups. That's like 28% of all venture capital in the US. So the demand for solutions in this market is huge, which is where you come in. And one of the most defining characteristics of the healthcare market in the US are the regulations that are in place, which cost millions of dollars a year for developers who fail to meet these regulations. So managing a healthcare solutions company can be very, very tricky. Security is not only a concern for your end users, but it's also a concern for the sustainability of your company. So last year was a record for fines due to healthcare data breaches. So more than $25 million in fines were applied to exposures or breaches of personal healthcare data. So these fines are applied by the US Department of Health and Human Services for businesses that have not taken enough care of protecting user healthcare data and have had it exposed in some way. So these kind of data is known in the industry as EPHI. It's electronic protected health information, and is one of the main things protected under the HIPAA regulation. So securing your users' electronic PHI is a small but important part of HIPAA, but it's also a whole system that involves other safeguards and requirements like access to buildings, policies and tracking, personnel training, and so on. So in this talk, I'll focus only on securing ePHI in a HIPAA-compliant manner, which should be the biggest concern for you as a developer. More specifically about how you can achieve the technical safeguards that HIPAA mandates around protecting ePHI. So right now, I'll give some recent examples of data breaches, so we can take a look at the underlying problem and think of a good solution. So the first one is Meditab, which is a company that processes faxes for healthcare providers. And their Elasticsearch database was not properly secured with a password. So with their data not being encrypted at all, they exposed over 6 million health records of adults and children patients. The faxes contained a bunch of personally identifiable information and health information. That breach was so bad, I'm going to take this opportunity to give a few examples of protected health information that you should never, absolutely never leak. So these faxes contained medical records, doctor's notes, prescriptions, amounts and quantities, illness information, blood test results, a whole host of information like payment data, personal data, and any information on children is also protected health information. So these are all protected under HIPAA, and it should never be breached. But this company leaked all of those. Another example is UW-Medicine, which is a University of Washington medical department, and they leaked information of almost 1 million patients. And they claimed there was a problem with moving data from one server to the other, and all the information ended up exposed to search engines. They had to work directly with Google to remove those search results. And WELLPOINT, which is an older case already settled, they leaked more than 600,000 patient records. And they claim this happened during a third-party software upgrade. So during this upgrade, their website stopped checking user identities and allowed anyone to access other patients, all of their patients' records. So they ended up receiving almost $1.7 million in fines. They had to pay that to the HHS. And the list goes on with these data breaches. There are even some websites that specialize in reporting on these data breaches, like Data Breach Today, HIPAA Journal, and the HHS Wall of Shame, which is where the HHS reports all the cases that they are investigating. So you don't want to end up in any of these. So as you probably noticed, all of these leaks I mentioned were caused by either misconfiguration, developer mistake, or third-party vendor failure. And actually, some industry researchers found that 80% of these data breaches are caused by those types of mistakes. So they're inevitable when you're storing or transmitting patient data unencrypted. The fact is, like, we put far too much trust into our database and servers, especially when they're provided by well-known third-party vendors such as Firebase and AWS. But almost all of the security we normally build is just access check. We check if the user is Bob, and then we give him access to Bob's data, and we think that's good enough, but it's not. We have the user devices and our EPHI in the database, and in the middle we have our backend doing those necessary access checks and serving data from our database as required. And of course, there are always ways around these access checks because of mistakes and misconfigurations. This is what's called securing the perimeter, and there's a huge problem in relying 100% on that. The data is still there in plain text, so you're still vulnerable to mistakes in these access checks. Leaks from the inside and kernel mode threats, which are design attacks which can read your backend's memory. You probably all heard of the Heartbleed problem, which was a developer mistake in OpenSSL, and who knows what can come next. So you need to be really careful about which platforms and services you're using to run your solution, and even then, anything can happen if you're just relying on access checks. If your patient data gets breached, at the very least, you can suffer heavy HHS fines. Your data can be held for ransom by hackers. It's actually the most valuable data in the dark web, in the black market today. And you can also be sued by your users who have been affected by your data leak. And the list goes on. No one wants any of these things to happen to their company. So how can you sleep at night knowing that a simple developer mistake or a vendor leak can damage your company? Well, in this talk, I'll go over a few cryptographic tricks that you can use to help simplify your security decisions without sacrificing usability. And I think one of the biggest sources of inspiration for balancing security and usability is Apple itself. And they're very open about how they handle security, and generally the rest of the industry tries to catch up. So they have this page called Approach to Privacy, and it's a good place to understand their philosophy regarding privacy and usability. And the main thing I will approach is, here is their usage of end-to-end encryption in their communication apps, iMessage and FaceTime. Which is the reason that when the FBI knocked on their door saying, hey, Tim Apple, we need this person's iMessage history. And the only answer Apple had was, sorry, the only way we can do that is to break into the user's physical phone. That's what the FBI had to do. They actually had to pay some hackers to break into the physical phone of the person because there was no other way. So this is a huge improvement over the perimeter security that I talked about earlier. You're not relying anymore on access checks. You're managing access cryptographically. So data is not reachable it's not readable in the database anymore. So even if it's breached, it's useless. It can only be read by the users with the right encryption keys. And over the next few minutes, I'll explain how this end-to-end encryption actually works and what else you need to know to implement it in your healthcare app. So end-to-end encryption works like this. Let's say we have a healthcare app for patients' follow-ups. So the patient goes to see the doctor, and then over the next few days, they'll chat about the patient's treatment, and this type of conversation cannot be leaked. So we're going to end-to-end encrypt. So in this case, we have Bob, the patient, and Alice, the doctor. The first thing they need to do in order to have a secure conversation that is end-to-end encrypted is to generate public and private key pairs. A public key is what you use to encrypt data for someone, and a private key is what you use to decrypt data that was encrypted with your public key. The second thing is they're going to send over copies of their public keys to each other so they can encrypt messages for each other. They need to keep their private keys secret so only they can decrypt their conversations. No one else has access to it. Once they have their own private keys and each other's public keys, they can begin their secure conversation. So now Bob encrypts his message with Alice's public key and sends over the encrypted message. Once Alice receives the encrypted message, she will decrypt it with her private key, and this process goes back and forth. So it's the same process for Alice as it is when she wants to send Bob a message. And this is cool because whatever a message goes through before reaching Alice or Bob, no one can read it, even if they bypass your access checks. So what does this look like in practice? First, let's see the high-level components of this puzzle. You have your iOS application and some kind of public key service and your IP messaging solution. First, you generate, the iOS application will have the job of generating a cryptographic key pair, and as well as encrypting and decrypting the messages. The public key service is where the iOS app will publish its public keys once it's generated, and will fetch the public keys of other users that it wants to communicate with. And finally, the IP messaging service will distribute the encrypted messages between users. So that can be Twilio, Firebase, and Nexmo, who are sponsoring today. So I'll only go into detail about the iOS application part, which is where most of the actual end-to-end encryption happens. And for the code, we'll need some kind of crypto library. Here, I'll be using Virtual Crypto, which is a very high-level open source library that fits our purpose. Also, it's for free and has a very permissive license. It's high-level enough that it follows basically my explanation. It's like Swift UI for cryptography. Okay, so again, first step, we generate a private, and public key pair. For that, we initialize the crypto library, super simple, and then we generate the key pair with a simple method call. Number two, we save the private key somewhere, so that key pair contains a private and a public key. So we save the private key somewhere. And in this case, I'm using, I think the slides gave it away, but you shouldn't use user defaults to secure your private keys. You should actually use keychain, but like the code for that is super huge. And but there are actually a few libraries, a few wrappers for keychain that actually make it very easy. I just didn't want to choose one. So number 3, you need to publish the public key in your public key service, and so other users can see it. So this is not part of the crypto library, so you need to build it yourself. That's a simple post to your service. And finally, you can, before you can encrypt the message, you need the receiver's public key. So you look it up on your service. So that's a simple get to your REST API or something that you build to store these public keys. So in this case, we get Alice's public key. And finally, you can encrypt message for Alice. So you turn that text into some data, and then you pass in the public key, and the crypto library does the job of getting that text into something unreadable. So if you have a good eye, you can see the public key is between brackets. And that's a cool feature of the Virtual Crypto Library, which means you can encrypt some text for multiple public keys. So you already have out of the box some kind of group chat, secure group chat. So if you're in a group, you pass in, like with 5 people, you'll pass in the public keys of the 5 people there, and they all can decrypt it with their private keys. And finally, if some data was encrypted with your public key with the previous method, you can just use your private key to decrypt it. And by doing this, you achieve transmission security, which is one of the technical safeguards that HIPAA demands. And apart from having transmission of data be encrypted, HIPAA also demands that the integrity of the message is kept. So I'll explain it with the following situation. Since the public keys are generally public, there's nothing preventing that a malicious player in between is intercepting those messages and encrypting something else with Alice's public key and sending that instead. So let's say Bob sends a hello to Alice, and the malicious player holds that message and sends instead, hello Alice, please send all my health information to this email address. And then she sends the health information, and basically, even with end-to-end encryption, data was breached, and you can receive a penalty for that. So through a little bit of hacking and social engineering, it can still happen. So the solution to this is what we call data signature, which is a piece of data that can only be generated with a private key, and it can only be verified with a public key. So it looks like this. You write the message body normally, and then you attach a signature that was generated with a private key, and you encrypt this data structure with the recipient's public key. And again, this is super easy to do with Virtual Crypto. Instead of simply encrypting a message with the public key, you will use almost the same method, but now you also add the private key to generate the signature. And same thing when you want to decrypt, it's also very simple. Instead of simply decrypting the message with the private key, you also use the sender's public key to verify his signature and assert that it came from that person and not someone in the middle. So that might seem like a lot, but you can see the code is very simple. If you use a high-level library, you don't have to be a cryptographer to get end-to-end encryption and data signing in your app. And with these two things, end-to-end encryption and data signing, we have at least 3 bases covered. So we're safe against database compromises because data can only be decrypted with secret private keys. We're safe against man-in-the-middle attacks because data is signed with, again, secret private keys and can only be verified with public keys. And if you use Virtual Crypto, you're also safe from brute force attacks because the underlying encryption algorithm used is non-deterministic, which means it can't be predicted. So if you encrypt hello, Dr. Alice, with Alice's public key, the encrypted data will look different from any other times you encrypted it. So 3 birds, 1 stone, database compromises, brute force attacks, and man-in-the-middle attacks. And you also comply with 2 technical safeguards that HIPAA demands. Okay, so now this is the part where most talks fail, but I'll do a quick demo, so fingers crossed that it works. It was working yesterday. Okay, let's bring up. Okay, let's bring up our friend Xcode. Okay, so I built this simple application for Mac OS, but it also works for iOS or Watch and all Apple platforms. So this is the dangerous part. Where is build? Did I press build? Okay. Pull it up. Okay, so this is basically the scenario I was describing earlier. You have Bob, the patient, and you have Dr. Alice, the physician, and they want to have this secure conversation. Okay, so let's go. Let's say Bob wants to say, hello, Dr. Alice. And the first thing he needs to do is to encrypt it with using Alice's public key. So you probably can't see much here, but it's like a bunch of garbled data. You can't understand anything of that. So we copy it over to Dr. Alice field, and we decrypt it with a private key. And it works. It just goes. And now we want to do the same for Dr. Alice. Hello, Bob. How are you? And then we encrypt it with his public key. And now only Bob, once this is in Bob's device, only he can decrypt it with his private key. Okay, hello, Bob. How are you? That's the basic flow. Now, what happens if we try to encrypt hello Alice, but then we try to decrypt it with Bob's public key, which he didn't use to encrypt this message with? It fails. There's no way to decrypt it with anyone's private key except with Alice's. And also I can show here that, let's say, we encrypt hello AltConf. So this is what it looks like. And then if we encrypt it multiple times, it's always different. So this is like the non-deterministic characteristic of the Virtual Crypto library, which means nobody can guess what's going on between Alice. So if someone encrypts something with Alice's public key, like say hello, and I encrypt it with hello, I can't do this comparison and guess what's going on. Okay, so demo worked. Let's go back to the slides. Cool. So again, you can find Virtual Crypto on GitHub, and it's 100% free, no buts. It's free, and you can use it commercially however you like. You can fork it. And it's available for a ridiculous amount of languages and platforms. So you can use it on Android as well, and almost any other platform. And back to our covered bases, this is just the basics, and it's pretty cool already that we're protecting against these 3 kinds of attacks and also complying with those 2 security safeguards. But there's a whole world of enhancements that can get other bases covered. So perfect for its secrecy is another trick on top of end-to-end encryption. And it means even if private keys are exposed, nobody can decrypt the messages because messages are now encrypted with short-lived keys instead of always the same public key for the same private key. But that's a whole other talk. So I'll leave links if some of you want to go deeper into it. And of course, end-to-end encryption and cryptography are not everything. There are other tools and considerations when building a healthcare app. Apple has built a whole suite that assists in collecting, sharing, and storing healthcare data. That's CareKit, ResearchKit, and HealthKit. And each of them has its focus and set of features. So HealthKit allows you to track users' vital signs and health statistics like weight, height, sleep patterns, food, blood pressure, blood sugar levels. It allows you to have secure access to health records from the user's healthcare provider. So that includes sickness history, allergies, vaccinations, surgery, lab results, and so on. So that comes directly from the user's healthcare provider, and that's something new that Apple has built using the FHIR protocol. So that's a HIPAA-compliant protocols for getting access to user health records. So it's ideal for apps that manage the user's ongoing health and fitness. And CareKit allows you to measure symptoms, track medications, get insights on how these medications are working with these symptoms, and it allows you to share that data with the patient's doctor team. So it's ideal for apps that deal with medical treatment. And ResearchKit, it's more focused on medical research, so it facilitates enrolling participants, gathering data, and you can share it with a whole host of researchers. So it's ideal for medical research. So if your app needs to collect and use some health data, you should consider using Apple's healthcare frameworks instead of collecting that data in your own database. And because Apple is doing it in a manner that requires user consent, so the user knows exactly what he's sharing with your app, and it also secures it, stores it securely, which these things are both part of HIPAA compliance. So if you're thinking of building a healthcare app and, or you are building one, I hope I've given you some useful insight on what's required of you in terms of security and privacy, as well as on the tools that you can use to achieve these standards. So if you have any questions, I think we have some time now, or you can find me later and ask me any question related to the talk.
Yeah, we definitely have time for questions. Let me get the mic over to you. What was it?
Yeah, hi. So I actually have two questions for you. The first one is, how do you deal with users that have maybe multiple devices they switch back and forth between, or I dropped my phone in the lake and now it's dead, and setting up a new device? Like how do you deal with private keys that are local and then having to change devices, stuff like that?
Yeah, sure. So there are like infinite ways of dealing with that. Each one has their drawbacks, and I guess the most naive one, and that brings less usability, is to just generate multiple private and public key pairs for each device. And that means if you have a conversation on one device, and that means you don't have access to history, because you can't decrypt. Once you add a new device, you can decrypt the old messages in the new device. I think WhatsApp does that. You can't read your message history. There are other ways you can, instead of generating a key pair for each device, you can use, our virtual crypto library does that. You can encrypt the private key, publish that private key securely, and use some kind of password. We have an algorithm that takes a password and encrypts the private key with that password and stores it safely on the database. And we call that brain key. So you can go to another device and then type in the password. It downloads the private key and decrypts it. So you have, that's very convenient for the user. So you can have access to all the old messages. Yeah, I think there are other ways as well, but these are the main ones.
So that feature that you were just talking about, is that in the virtual library itself, or is that a separate library?
Yeah, the algorithm is there. So you're also going to need to build a service to store the encrypted private key.
And then my second question was, what kind of import-export restrictions, things like that, like exporting to different countries, like do you have to limit where the app is for sale, market as having, cryptography and stuff like that in the app if you use like the virtual, library and stuff like that?
I'm not sure if I understood it correctly. Do you mean like from a regulation side?
Yeah, so like when you upload an app to the iOS App Store, it asks you, do you have encryption built in? And if you do, then there are certain regulations and stuff you have to comply with, and there's all kinds of paperwork and filings. And I didn't know, with some libraries you can kind of get around that. I didn't know if Virgil had those requirements and if you have to do that or what.
Yeah, so you definitely need a compliance expert for each country that you're going to publish your app in. Some countries say like, hey, you can't store, like, I guess Canada, but I'm not a lawyer, so don't quote me on that. I guess they don't allow you to store any kind of data, even encrypted, outside Canada for Canada patients. But yeah, like Virgil Crypto is going to help you build the cryptography side, but you need to also keep in mind that there's a whole other host of security for compliance measures that you need to take.
Cool, awesome. Well, thanks for the talk. It was very interesting.
Thank you.
Anybody else? Oh, here we go.
Hi, you said your algorithms for encryption are non-deterministic. What are the names of those? Which algorithms does Virgil Crypto Library uses?
Okay, so maybe I can. So our crypto library is like, it's agnostic of any algorithms. You can actually use the algorithm you want. Let me see if I can bring up Xcode here. Okay, so maybe I can show you how you can like choose your own algorithms here. This is hard to see. So of course, in the library README, you can find all the algorithms it supports. Try crypto generate. Of type. Okay, so you can like here you can choose your own algorithm for this private key. The default one, I'm not exactly sure which one it is, but we always use like the latest and most battle-tested algorithm for the default one. And you can find which one that is in our README. And I can't speak for the cryptography side too much, but there's some randomness added into the blob that makes it non-deterministic, and that's accounted for and taken out once you decrypt the message. So that's how we protect against brute force.
Okay, let me get the mic over to you.
Take the mic.
Yes, you illustrated how the encryption generates two different constructs, but they're both decrypted correctly. Something about that doesn't make logical sense to me, since you're using the same public key and the same private key to generate a variety of encrypted messages, and somehow they're different, and the reader is using the same public key and the same public key. So how is that parallelism?
So you mean
explained?
from the non-deterministic thing? You mean like it's generating, like I say hello AltConf, and it's generating multiple different things?
That's right.
And I decrypt it with the same private key.
That's right.
So I didn't implement like this solution, but what I know from it is that we add some randomness to the payload that is decrypted, that is encrypted, and once we decrypt it, we transparently remove that randomness out. So
Oh, I see.
yeah,
I understand.
so this like is a good protection against brute force.
So the message you're actually sending is a message that the user created plus something else
Yeah,
that's
plus
random
something random.
that you can isolate from the message.
Yeah.
So when it's decrypted, it gets two pieces, and the receiver gets the same random. How does the user know which is the random thing you added? There's some way of identifying
Yes,
it
there's
and carving it out.
yeah, there's some way of doing that.
Okay, that's very clever.
Yeah.
Going back around.
So you mentioned that you stored the public keys in, say, a server. That's going to be your repository for the public keys.
Yeah.
How do you prevent the hacker in the middle from replacing the public key from Alice so that they can start sending messages? I'm wondering about the HIPAA side of it. Like, Alice has to be able to change her public key eventually. How do you distinguish between that and a hacker trying to replace the public key?
Okay, so of course you have like your normal authentication, and you're only going to publish it if the user has the right token for Alice. And of course it can be replaced. Like as I said, that is still perimeter security, and someone can go there and access the server directly and replace it. And that's something that data signing is going to protect against, because even though you changed Alice's public key there, she still has the same private key. So if someone encrypts the message with her new public key, she's not going to be able to decrypt it with her private key, and she'll know like something wrong is going on.
Nobody could send messages pretending to be Alice is what I'm getting at.
Yeah.
Okay.
Yeah.
Okay.
Okay.
Any other questions? All right, thank you.
Okay, thank you guys.